So today's tutorial is a bit of a longer one, and it's one that I really want to put out there because when I was early starting as a coach, often the kids would go on to YouTube and find some really great tutorials around line following, but when they actually came back to use them at school, they'd often find that there was a lot of issues with a few main things. They thought that the line follow code was just going to work straight away, and a lot of people are showing the video of it just doing this magical, beautiful line following without actually going through the process of debugging and obviously showing all the steps that it took to get to that point in the first place. So what I really want to go through today for a lot of kids that are starting out, and for teachers especially that are wanting to be able to go there with kids and to be able to have this level of knowledge to be able to support them, is to go through the steps to, well, what is it that we're trying to achieve in the first place. If we come back to the idea of computational thinking and breaking stuff down into problems in smaller steps from bigger problems, like there's a lot going on in line following. Obviously when students see it, they're just seeing the fact that the robot is potentially following a line, but what I really want to get them to a point of appreciating is, well, how is it doing that in the first place? What did it do to be able to firstly find the line, and then from there, what did it do to be able to continue to do what it needs to do? Like, how does it keep going around some of those tighter bends? How is it going to stop potentially when it gets to somewhere where it needs to stop? So this tutorial first of all would just be for the idea of, let's just get them following the line to start off with, and then from there we'll move on to how can we use some different exit conditions to be able to get them to stop as they go. So if we break line following down into what we would probably call so the part of that computational thinking and looking at the patterns itself in the first place. Obviously we've got black and we've got white when we're following most of the lines. The interesting thing with things like FLL and some other competitions is this background color isn't always predictable, and in some of the situations, especially if you were part of the season we're into orbit, where we had this really dark navy color in contrast to the black, there really wasn't that much difference between the two colors. So the robot was really struggling sometimes, especially with without looking for what we're going to introduce in a second is called grayscale. It was really difficult for kids to be able to use color as a way of differentiating, to be able to sort of bounce off the line, to be able to follow along. And that's the initial sort of one that we start to go through. I'll just make another copy of this. And if we imagine what we're trying to achieve in the scenario where we're line following to start off with, and it's kind of like a zigzag pattern that we'll get, and that's one that I'm going to introduce here to start off with, is where the robot sort of bounces off the black, sees too much white, bounces back to the black, white, black, and it just keeps going along as it goes. So it's a really useful line following technique for when the students are first starting out, and it still is useful later on, even when we're doing things like firstly acquiring the line. And with a lot of tutorials, that's the main thing that they're missing. Like, how do we actually get the robot to the line so it can follow in the first place? So what I want to point out first and foremost is that we need to know a bit about our robot. We need to know about what it can see currently. So if I just come back into the Spike software already, at the moment it's set on color mode. What I really want to push, especially for students that are starting to get up into that upper primary bracket anyway, is starting to really understand this idea of reflected light intensity. It is a science concept we explore in the Australian curriculum, so they're aware of the fact that there's light is being able to be reflected and absorbed, and it's a really, really cool way of showing it in a practical scenario. So at the moment, even with the dim lighting that I have in here, I've got 98% of the light is being reflected back on white. So I'm just going to record that in here. And let's just have a look now. If I put that onto the black itself, what have we got now? We're coming down to 16. So 16% of the light is being reflected on black. So what I want to do now is just show you a simple algorithm. We'll make this a bit bigger so we can see what's going on here. To be able to figure out what I was talking about before with grayscale. So wherever black and white meet, obviously we're not going to be able to see it at the best of times. Our eyes are good, but they're not this good. To be able to see where those two colors meet, they mix. And often what we're going to find, or not often, every single time we're going to find, there is an element of gray. And it's a lot easier for a robot to be able to follow these concepts of grey than it is to be able to make a decision based on colour, because the colour sensor that we've got, it's good, but it's relying on making your best guess. And not always, especially when we're talking about before how we had a dark navy and a black, is it going to make that best guess. It's just going to assume based on the mixes of mixing the R, the G and the B together, to be able to just try and guess what color it is. So if we just let it guess, sometimes it's going to be wrong, and in a competition that's not what we're chasing. We want it to be perfect every single time. So what we're going to get here is we've got white, we've got black. What I'm going to do is just add those two together, and then I'm going to divide them by 2. And I'm just going to write the algorithm down here so we can use this later on. And this will work for pretty much any robotic system, and I've used it even with line arrays where you've got up to 5 or 6 different sensors. You could do this same algorithm for each different sensor and then feed all that back together as it goes. Average of 57, and that's the target later on that we will use to be able to get our robot to follow perfectly in between the white and the black. So, but let's go through the steps first. I'm just going to delete this one here. Our robot is currently over here. It might have just started something on the FLL table, for example. It's just done a mission. We now want it to be able to come over here and follow a line to another part of the table. So first and foremost, this robot needs to make its way to that line to start off with. So we're going to need a little bit of code to actually get it there. So if I put another little square over here and I say that I have a color sensor on this right hand corner, and I'll just make the color a different color, and this color sensor is the one that's feeding in the data that we want to try and collect. So we're just going to get the robot to simply drive forward until this color sensor hits black. And if we were on a simple mat where it was white and black, we could just use color for that particular thing. But what we've discussed now is the fact that, well, with reflected light intensity, we've got it's 98% on white, and then it's 16% when it's kind of in the middle of the black. The other number that we've now suggested down here is that is the average between the two. So if we ask the robot to drive forward until it saw something potentially lower than the average, we know that we've kind of stopped about here. Rather than going all the way over, we're trying to stop here, so when we actually do ask our robot to make a correction to be able to follow the line again, it's not making the correction over here and potentially skipping off and starting to drive around over here in circles. We want to stop it here, so then it can quickly acquire the line to be able to start to do that. So let's just work through that as a starting point now. So for this particular robot, this is, I think it's build 3 of the competition series. It's also got the color sensor obviously on there as well. We've got the color sensor in B, C and D are our driving motors, and E is our accessories motor. What I've also added to this build is part of a suite of stuff that I'm just developing at the moment, is just some stability. And you'll see I've added on a couple of beams, just some 5 beams on there, so it just stops the tipping of this particular design. Not necessarily for what we're doing right now, but when we start to add weight and some other attachments on later on, it does make a difference with the stability. So all I'm going to simply do is, I don't want the robot to drive very fast while it's doing this, so we'll just set the movement motors first. And obviously we're relying on a sensor for data, so we're not going to drive for rotations or anything. We're just going to simply say here, start moving forward, and I'm just going to set the speed at the start here to potentially a low speed. So I'm just going to say 20 to start off with. Obviously in competition time matters, so later on as the kids start to progress through this and they start to have a bit more success with it, they might try creeping up to 25 to 30 and just seeing how the robot responds to that little bit of extra speed. Obviously the faster they go coming in, they have the negative if they're going to overshoot sometimes and potentially be in the middle here, and that will stop them from being able to do what they want to do. So we want, just as best as we can, try coming in slow, and I'll jump back into here. So all we're going to do now is just put in here, and probably the easiest way to do it is to say just start moving straight and then wait until, and if we come down here now, obviously we've got our color, and the fact that we're using the triangles now, wanting to use the triangles as well, so the bowline will come down here, and my color sensor is in B, and we said before, if I come back to here, that our average was 57. So if I come back to here and I say anything less than 57, and then I'm going to simply get it to stop. So let's just try that for the time being. Okay, perfect. And it's stopped. So if we just try that again, and I try it on a different angle, so potentially even a sharper angle. Okay, see there, the interesting thing on this mat here is we've got the red. So what does it read on red? It reads 54. So yeah, so we can see how the difference between there, it actually still shot over the black. So even if we, and if I bring this right in closer, we could potentially even ask it to hit a target that's less. And this is where obviously the board that you're using would really impact on these targets that you're trying to hit. So for example, keep coming back to that into orbit board, having that dark navy and black, there probably would be very little difference between some of them. So it would be really pushing then what is it that we need it to be able to hit. And this is part of the stuff that I really want to emphasize. If I just followed a tutorial online and just said this is how you line follow, the kids don't see any of this initial tuning and understanding of, well, why is it doing what it's doing. So this number here would always need to be tuned, and I'll just put that comment in there, tune to board. Oop. Okay, so all of this here now is our find the line basically. So if I wanted to try and get the kids to start understanding how the functions simplify these processes, I'm just going to come down here to my blocks now, and I'm just going to make a my block called find line, and I'm just going to click save. So I don't need to change anything more over here. I'm going to leave my move motors there at the start, sorry, just for the simple process of the fact that that's going to maintain the same throughout any of my codes. So find line is as simple as set the speed to 20, move forward until we see that sort of average between white and black, and then we're going to stop. So I'll just drag find line now over here from my mind blocks. I'll just make sure that works again, so I'll bring him over. Beautiful. Okay, so from here, this is the other challenging thing. If we were just tell the robot straight away that we want it to line follow, it's going to have a fairly hard time, especially in the position where it is here, where it's got a decent sort of curve to come back around. So if we did the bounce off technique here, what I'd simply suggest for students is we find the line as we drive in, and then what I want to see, I'll just turn those motors off. What I want to see now is that obviously this initial line follow will need to be a little bit more severe or a bit more reactive than normal to be able to get our robot to sort of kick around to be able to get back onto the line. And I am going to use that simple tap method to be able to do that. So what I'm going to do is I'm just going to move this my block off to the side for the time being, and I'm just going to bring in a forever loop for the time being, and that's mainly just because that we're testing at the moment. We used over here this reflection block, and all I'm going to do now is just duplicate that here now, and we're going to say that that's obviously the middle ground of where we are for what we're trying to achieve, and that's this dead sort of center between the black and the white. So if it sees anything less than 57, we know it's on the black. So it's come in, it's stopped now. So obviously to get away from the black, we need to turn in the other direction. And the easiest way to turn is to turn this motor here on and turn the other one off. So all I'm going to get it to do now is turn this motor on until it gets around. An even more severe way of turning, or a sharper way of turning, would be to actually kick the other one backwards. And we can see that tank turn now is coming out, and we can do that here if we want to. So what I just want to get through here is there's a couple of different ways of doing it. Speed is a interesting thing to use with line following, because speed, anything where we're saying speed, we're trying to make both motors work together simultaneously in parallel. So if one is running at a set speed, it tries to do the exact same to the other. And often we're not wanting that in line following. We're wanting this particular motor sometimes to operate at a different speed to what this one over here is, because we're wanting it to be quite agile and quite nimble. So if I come down here, I've already done that, and I'll just quickly show you how I have done that. I've already added in some extensions, and the two extensions that I've added in are more motors and more movement. And these extra extensions will give us a little bit of play, and especially this word here, this idea of unregulated power. So, and that's where it's saying that it's not trying to maintain through an algorithm the set power that those motors are achieving constantly. It's just saying, I'm going to give you this power regardless of what's happening to you. I'm just going to try and give you that power all the time. I'm not going to try and control you at all. I'm just going to let you have that power. And that's a really good one with students to understand for like vehicles and stuff later on as they progress as well. So all I want to do now, obviously we said earlier we wanted to turn one motor on and one motor off. If I come back up here to the normal motors, I can see that I can do some of that sort of stuff, but it's all in speed. So if I come right down the bottom now, we can see we've added in these additional blocks where we've added in those extensions. So this one says more motors, and this one says more movement. So I can see here now I have this block here which says start motor at 100% power. So what I'm going to do quickly is let's just have a play. If I pick this robot up, I want to just understand a few things. If I turn this left wheel, I'll move my mouse out of the way so we can see, and I move it in a forward direction, it's actually going backwards in the amount of degrees that it is maintaining. So what that means is to go in a forward direction, I actually need negative power. And that's something interesting with this particular block in general, is that it doesn't understand, and that's where these pink blocks are doing all this mathematics and stuff for us, because they are actually regulating the fact that this motor has negative power. So if we look at C, and I'll just show you now, if I actually told C, let's just drag this out of the way for now. If I actually told C to turn on, let's just say 20% speed now, what we'll actually see is that this robot should drive backwards. Yeah, so it's going backwards as it goes. It's got stuck on a little hump there. I'll just press play again. And that's just the other interesting thing. Power with these motors, it doesn't like anything lower than 20. So it's actually just stalled there. So if I press 25 again, I think 30 is generally, especially if there's any kind of load on the motor. So if the students are asking it to drive quite slowly, typically anything that we're going to do with power is going to be 30 at the least, especially when there starts to get weight onto a robot, or it's moving attachments around a board or doing other things as well. So giving it positive power, it really should drive forward, but it does the exact opposite. So if I flip that around now and I say I want to give you a negative power and I actually want you to drive backwards, we're going to notice a weird thing now is that the robot actually drives forwards. So we need to understand this when we are building that line follow algorithm. Typically what I would recommend with my students here now is that I don't want them to be feeding in negative numbers. I don't want them to be having different integers as they're working through that, because it just complicates things on a level that we don't need to do. What I generally try to push early understanding of, even with the younger kids, is this idea of, and especially within the mathematics within 5 and 6, is multiplying by a negative number will actually give you a positive number. So if I feed all of the same speeds into here. So if I just come back to 0, for example, all I've grabbed is from our mathematics blocks is a multiplication, and all I'm doing is I'm timesing it by -1. So if I put this one in here now and I just put in 30, obviously if I multiply a positive number by a negative number, I'm going to get a negative number. So all of the students are going to see is they're putting in 30, 30, 30, 30. They're not putting in negative 30, 30. So it's a very good understanding and a very early thing that they can do, and it's something we'll feed into later on when we start to make a little bit of a proportional line follower. Is that's a great way to get them to understand that even though these motors are the same, if we actually looked at how they're positioned, this one has then been mirrored, which means it is backwards. Because they're the exact same motor, they rotate the same way. It's now that we've changed its position, that's why it is traveling in a negative way to be able to drive forward. And that's another thing with using these pink blocks all the time. The kids don't actually understand what those blocks are doing in the background. So it's great to be able to get them to start to play with these, because in most other robotics applications, if they work into Arduino and some of the other things like that, this doesn't happen for them. They need to start thinking about how they will do this themselves. So if we start to go through now, this was C motor, and we know that this one said if it sees black, basically, or that line between black or grey. So if it sees that grey, it's going to turn the other way. So all I'm going to do now is duplicate this. I'm going to get rid of that, and I'm going to change this to D. So D is our right motor, and if we power on our right motor, it's going to move away from the black and it's going to come back to the white. So the loop will come back around and it'll say, hey, I'm not on black anymore, so I'm going to come down here, and then this wheel will kick in to come onto the black, and then it'll keep going around as it goes. So what we should see now, let's just see what happens here. Again, let's just try what we had before. I'm going to ask the robot to drive in, find the line, and then follow the line. Let's just see how savage this is. So I'm going to put the interesting thing we've done here is we've turned motors on, we haven't turned them off. And let's do that now. So whatever motor's turning on, we want to turn the other one off. Did find the line pretty well to start off with. Yeah, that's looking a bit better. Just going to start on my paper. So we've got a zigzag line follow as it's starting to go through. So what I'd suggest here now, and let's just try it again here on this, like do a much sharper angle, so coming in pretty much dead straight. Yeah, so that's not enough to be able to get it to kick around, so we'll just try that again. Oh, it's just... So what we can do here now is, let's increase the speed at which it's reacting. So let's change that to a 50 and to a 50, and let's just see now what happens. Okay, we've got a much quicker response and a lot more wiggle now. So my suggestion is that we break this line follow down into 3 parts. So we've got the first part being, let's just do this in here now. First is obviously we need to find the line. The second is we need to acquire the line. And by acquire, I mean that we actually need to make sure that our robot is in a position where it can actually follow it. The last part then is obviously we want to follow the line. So really, in a perfect situation, we would see that a good line follow code would do all 3 of these things. It would have something in there for the students to be able to find the line. The second part would help them to acquire the line, regardless of how sharp the correction wouldn't be to get there. And the last part is then we need something to be able to follow the line. So what I'm going to suggest for this part here is, rather than using a forever loop, so I'm just going to get rid of that forever loop, I might put it over here for now. We're going to follow this, we're going to have this correction for a period of time. So just for a quick, short, little sharp set thing that we're going to do. So we're just going to say here, if I come down to sensors, we've got these two here now that say timer, so I'm going to drag them both out. Unlike the EV3 where we had access to about 8 different timers, the Spike only has access for one. It can run multiple through using variables and some other different things, but as we're starting out with kids early on, it's a good idea just to get them used to using one at the time anyway. So what I want to do here now is I want to say that if this timer is greater than, oh, I don't even know, let's just say half a second or 1 second to start off with, I actually want this initial loop to stop. So this really quick correction to stop, and then we can move on to the smooth stuff later on. So what I could do is just duplicate this, bring it over here, and obviously we've got the two different speeds here now. So if I wanted it to follow after the initial correction, I could bring it back to that 30, and I could have a lot less of a really abrupt correction. And for that initial acquiring the line, I want it to come down here to operators, and here we need to use some more of our maths. So we're going to say here, we're just going to say here, if our timer is greater than 1, we want it to stop moving. So let's just have a go here now. So it's going to count 1 after it finds the line. Okay, so it's done pretty well. Let's try the other side where over here where it's got to come into the line. I'll just play it again. Yeah, so we're a lot closer and a lot more aligned to where we need to be. I might even do that for less. Let's just say maybe half a second to see if that makes a difference here now. And what I'm going to do is press play again. Yep. So as we did before, I'm actually going to turn this part now into a my block, and I'm going to call this part acquire the line. So I'm going to come down here to my blocks, and I'm going to make a block, and I'm going to say acquire the line. Doesn't need any other inputs or anything at this stage, and all I'm going to do is come up here, take it out of the way, so the students don't need to worry about any. Oh, what am I doing? Okay. So what I could do is even structure it so when the kids see it, oh, let's bring this down, that they see it in the sequence that it travels in. So here's find the line, here's acquire the line, and obviously down the bottom here we're going to have the line follow itself. So I'm just going to make another block now as well, and I'm just going to call this follow line. Done, and save. We've got follow line there, and we know this works because obviously we've just tested it, but this is at that reduced speed of 30. So what we should see here now is we're going to find the line, acquire the line, and then follow the line. Obviously we've got a forever loop here, so it is going to go forever. I've got it driving in, and then it's done the acquire, and now it's doing the follow. So I'm just going to get stuck on that piece of paper again, and it's now following all the way through. So I'm just going to come back now, and if we go through what we've done, so acquire the line, find the line, sorry, acquire the line. All I want to do now is try and make that acquire a little bit sharper. So what I'm going to do is I'm going to come over here, and rather than saying stop the motor, I'm actually going to give the motor a negative power. So I'm just going to duplicate here and duplicate C. So C needs to go up there and D needs to come down here. So with this C motor, because at the moment we're trying to give it positive power, so we had positive 50 and positive 50, I was going to drive in a straight line. We want it to turn now, so I'm going to have to give this a negative power. So I've got 50 in one wheel and negative 25 in the other, and I'm going to do the exact same thing underneath. And what we should see now is that the robot can turn with a little bit more little bit more sharpness, and hopefully we should be able to see it not so much on the black. Yeah, that was perfect. So if we just show that again, it was able to come around pretty quickly to be able to acquire that line as it went. And we're on a fairly steep angle here now to be doing that, so that's a good way of being able to get around anyway. So that as an entry level, and I know it's still pretty full on for an entry level, it's just more understanding than obviously the parts that are taking place. So we've got find the line, drive in pretty slowly until it sees that grayscale, or the average between the two. We've got this first little part here where we acquire the line. We probably could now even remove these stop motors, because we just want to see it really sort of flow through those two stages now. So, and then into the final line follow portion. So we'll just give it another go here now with that stop motor in there, and just see how, if it makes too much of a difference. Yep, it's a pretty solid acquire, and then off it goes. So from here, that's probably a great place for most students to sort of work through and to work to. If we take it a little bit further from that, it would be, how can we get this follow line now to be potentially a little bit faster, not by necessarily increasing speeds, but by making it smoother. And I'm just going to make another my block. I'm not going to replace this one. I'll leave that there as well for people to be able to go through. But what I want to try and build now is something called a proportional line follow. So it's a process where we're looking at potentially giving it a set target or a set point that we want it to be at, and then allowing the robot itself to make the turn adjustments that it needs to do based on that target. So if we just quickly make another forever block here, I'm just going to build it down here underneath. There's a few things that we need to do to add into this, and for students that are working in that early secondary level where they're starting to look at functions and variables in a more dynamic way, this is a really great introduction to that. I'm going to introduce a variable called error, and the other variable that I'm going to introduce is called correction, and these two will work together. So before I do anything else within this particular code, I'm going to make sure at the start of the code I always reset those variables to 0. So before it actually enters in, it doesn't have it already doesn't have numbers or anything stored in those variables, because that can make my robot react really abruptly or erratically when it doesn't really need to. So there's a few things that I want to do here. I'm just going to grab 2 of these, and obviously the first one's going to be our error, and our error is based on a idea of a takeaway. So we're going to grab a minus here, and what we said before is the target that we want our robot to be at is that grayscale, or the idea of the fact that this is the average, so 57. So if we come back here, we're going to minus 57. So that's where we want our robot to be. Now what we're going to do is just come into here where it says the color sensor, and it just says reflected light. So it's going to take whatever reading it's reading, and it's going to take 57 from that, and that there is the difference between those two numbers is going to be the error. So whatever the error is what's going to feed into the correction, and the correction is then going to feed into the motors to be able to turn, to be able to fix this error. So in this correction part here, what we want to be able to do is tune the robot to, as we did before when we were adjusting, I'll just move that out of the way, adjusting the speeds up here, how quickly or how sharply the robot actually corrects the amount of error that it has. So all I'm going to do in correction here is come back over to variables, and I can see now I've got this little circle one here for error. I'm just going to quickly drag it down into this left hand side. On the other side here now, I actually want it to, and it's a personal preference for this, obviously this is another thing that the students will need to tune, a little bit less than what it's currently reading. I'd kind of like a smoother, slower line follow to be able to go through, especially when the kids are learning. So what it will actually do is it'll make whatever it's reading here if we times by a smaller number or a decimal number here in 0.8, it's actually going to be less than what it's reading up here. So we don't necessarily always want it to be super reactive, but in some situations we could use this particular code to also be the acquire to line and simply increase this particular number here to be able to get it to turn a little bit quicker. What I'm going to do now, however, I'm just going to steal these two blocks from over here. So these are both of our motors. And what I'm going to do in here now is I'm going to do a plus and another minus in here to be able to do a couple of different things. And this is called a linear equation. And what we're trying to get is that obviously we want a speed in here. So our speed is actually going to be determined on this left hand side. And again, I'm just sticking with 30. So it'll have a default of 30 speed, but there's going to be times where we want this robot to correct. So rather than just driving straight, it needs to either turn to the left or turn to the right. So in that situation there, this error will feed back in, and obviously correction comes in, and it could be a negative number, for example. So if we were feeding in, or even if it was a positive number and it came back with an error of 8, this particular motor would then have 30 plus this correctional error, 30 plus 8, so it would be 38, so D would be moving at 38 speed, but then this one here would be 30 minus 8, so it would be moving at 22 speed. So what we would see is that it would actually start to lean to, so D is on our right hand side, it would actually start to lean to the left because the D motor is moving faster than the left motor. So what we're seeing now is that based on this error is the severity of the correction. So the bigger the error, the bigger the correction the robot will make. So obviously we need to feed correction into this other part down here. So I'm just going to grab the other little circle one and put it in both sides. And we know C motor actually moves backwards. So the interesting way of testing this here now is if I just take all that off and pop that on, if the robot drives backwards, okay, I'll just come back. Okay, so it's following on the outside of our line. So to change that, all I'm going to simply do is to swap these turns around. So the negative will go up here, and that will follow on the inside of the line. And already you can see that if I follow from back here, it's a lot less wiggly than before, but it still is quite wiggly. So that 0.8 even is too much. So I'm actually going to reduce that down to 0.6. So I'm going to press it again now. Perfect. Very smooth. Corrections are hardly even noticeable when it's following through. And it's able to drive around there really well. Obviously it's getting stuck on the paper. Right. So there is a proportional line follower, and what I'm going to do now is that becomes an alternative to this. So what I'm going to quickly do is make another my block, and I'm going to call this one, I'm just going to call this prop line follow, and I'm going to save that. What I really encourage the students to appreciate is there's going to be situations where this line follower is actually better than this line follower. So it's understanding when to use what and making sure that whenever we build any of these codes, we don't just delete them, we've got them there if we need them later on. So I'm just going to drop the line follow out and show the difference between the two now. So if I just do the exact same thing we did before, press play, we've got find line, acquire line, and then proportional line follow at the end of that. Beautiful. Let's try it on this other side. What we could see then is that acquire the line is still too long. So let's go back over here. Let's change back to 0.7. Let's try 0.4 now. Beautiful. Nice and smooth as it goes through. So a few things for students to be able to go through and to trial there. So making those, there's 4 there now, to be able to get to a point where we can have all of those different components to be able to use at any time that we want to, and we know now that they're all working as well. Obviously those 3 could then become their own my block again. So if we just put in here line follower and click save, what we then can is actually add those 3 functions into that, and then just simply say I want to line follow. So rather than having to do multiple codes, boom, it's able to do all of them together as one block, and we can just keep reusing that, reusing that, reusing that whenever we want to. So hopefully that helps in starting up the line following process. There's a lot of stuff there for the students to be considering, and especially when they start to go through and tune some of those numbers, there's a lot for them to be thinking about as they go through. But really make sure that we're sweating the small things within these particular things, especially that grade scale. It's a very, very handy thing to be able to learn to calculate. Hope that helps.